Welcome. You have arrived at a good place to rest tonight. If your mind is still moving through the events of the day, still rehearsing conversations or turning over small worries, that is completely natural. The mind does that. It likes to keep moving long after the body has stopped. But tonight, there is an invitation waiting for you, a quiet one. You don't have to accept it all at once. All you need to do is let your body soften just a little against whatever is beneath you right now. Let your shoulders release, let your jaw loosen, and when you are ready, let your attention rise slowly upward, past the ceiling, past the roof, up through the dark air above your home, and out into the sky itself. Because the sky is there tonight. It is always there, whether clouds are covering it or city lights are washing it pale. The universe beyond remains exactly as it has always been. Patient, enormous, quietly going about its business while you sleep. Tonight, we are going to wander through that universe together, not rushing, not cramming in facts or racing toward conclusions, just drifting, the way a thought drifts when sleep is beginning to come. We are going to visit some of the strangest, most beautiful truths that science has uncovered about the cosmos we live inside. Some of these truths are so large they resist being fully held in one mind, and that is fine. You don't need to understand every detail tonight. You can let the images come, stay for a moment, and then slowly dissolve as you sink a little deeper into rest. There is something particular about space that makes it such a perfect companion for falling asleep. It is enormous, yes, but it is not loud. It does not ask anything of you. The universe has been expanding quietly for nearly 14 billion years without requiring your help. Billions of galaxies turning slowly in the dark, stars living out their full lives over millions and billions of years, with a kind of profound, unhurried patience that most of us have never experienced firsthand. In its own way, the universe is the most restful thing in existence. And tonight it is simply letting you look. So let your breathing slow, not forced, just natural and a little slower than before. And let us begin at the beginning, or as close to the beginning as human minds have been able to reach. Roughly 14 billion years ago, there was no space, there was no time, there was no darkness waiting, because darkness itself requires space to exist within. What there was instead is something that our ordinary language doesn't have a word for. Physicists call it a singularity, but that word is really just a placeholder, an admission that our current understanding reaches its edge and goes no further than the moment before the universe began. The laws of physics as we know them did not yet apply. The familiar forces, gravity, electromagnetism, the forces that hold atoms together and push certain particles apart, had not yet separated into their individual identities. Everything was compressed into a state of almost unimaginable density and heat. And then, in a fraction of a second, so small that no ordinary number can meaningfully describe it, everything changed. Space itself began to exist. And it didn't just expand slowly outward from some central point, the way a balloon expands from a single spot. It expanded everywhere at once. Every point in that newly born space was moving away from every other point. There was no center to the explosion, because it wasn't an explosion in the usual sense. It was more like the sudden appearance of distance itself, the birth of separation, the birth of space, which meant, simultaneously, the birth of time. This event is what we call the Big Bang. And even now, 14 billion years later, the universe is still expanding from that moment. Space is still stretching. Galaxies are still being carried apart by the growth of the distances between them. Not because they are moving through space so much as because the space between them is becoming more. You don't need to picture this precisely. Let it be an impression, a gentle, vast unfolding. Something opening slowly and continuously, without end. In the very first seconds after that beginning, the universe was almost unimaginably hot and dense. There was no light yet that could travel freely. Instead, the early cosmos was a thick, bright fog of energy and elementary particles, all tangled together, constantly colliding and annihilating and forming again. Protons and neutrons began to assemble themselves from smaller components called quarks, simple atomic nuclei, hydrogen and helium mostly, formed in the first few minutes. But actual atoms, with their electrons settled into stable orbits, did not exist yet. The universe was still too hot for that. It took about 380,000 years for the temperature to drop enough for electrons to settle down with their nuclei and form the first true atoms. And when that happened, something remarkable occurred. The fog cleared. For the first time since the beginning, light could travel freely through space. The universe became transparent. And that first light, that ancient moment of clarity, is still with us today. It has been traveling for almost 14 billion years. It has stretched as space expanded, from visible light down into a much gentler form of radiation. Today it fills the entire sky uniformly, in every direction, as what physicists call the cosmic microwave background. If you could see in microwave wavelengths the way you see in visible light, the whole sky would glow with this faint, ancient warmth. It arrives from every direction equally. A whisper from the very beginning. Astronomers first detected this background radiation in 1965, somewhat by accident, when two scientists named Arno Penzias and Robert Wilson kept finding an unexpected hiss in their radio antenna, no matter which part of the sky they pointed it at. They initially thought it might be due to pigeon droppings inside the instrument. It was not pigeon droppings. It was the echo of creation. Let that thought settle for a moment. The warmth of the universe's birth is still present, still arriving, still surrounding us on all sides. You are bathed in it right now, even as you lie still in the quiet of your room. Light that has been traveling since nearly the beginning of time is passing through the walls, through the roof, through you. It carries no harm and makes no sound, but it is there, constant, patient, old beyond measure. Let your body sink a little further into rest as you hold that image softly. After that first light, hundreds of millions of years passed in relative darkness. The universe was filled with hydrogen and helium gas, spreading slowly outward, cooling as it expanded. There were no stars yet. No light except the fading glow of that first ancient radiation. Astronomers sometimes call this period the cosmic dark ages, and the name is apt. The universe was quiet and dim and almost featureless for a very long time. But gravity was working. It never stops working. In the slight variations in the density of that primordial gas, regions that were just a little denser than average began to pull surrounding material inward, slowly accumulating mass. Over millions of years, these concentrations grew. Gas clouds grew larger and denser at their centers. And then, at the core of one of those great collapsing clouds, pressure and temperature rose high enough to trigger something new. Nuclear fusion. Two hydrogen nuclei, moving fast enough under enormous pressure, can fuse together and release energy. And when that threshold is crossed at the heart of a collapsing gas cloud, a star is born. A point of light appears in the darkness. The first stars in the universe were probably quite massive, and they burned through their fuel relatively quickly. When they died, they scattered the heavy elements they had forged back into the surrounding gas, enriching it. From that enriched gas, later generations of stars formed. Stars like our Sun, surrounded by disks of leftover material that slowly gathered into planets. We are, in the most literal and precise sense, the product of that process. The carbon in your body, the oxygen in your lungs, the iron in your blood, these elements were not present in the early universe. They were made inside stars, in the nuclear fires at their cores, over millions and billions of years. And when those stars ended, they released those elements into space. Several generations of stars lived and died before our solar system formed 4.5 billion years ago from the remnants of those earlier stellar lives. You are, right now, a collection of atoms that were forged inside stars. You are, in the most genuine and non-metaphorical sense, part of the universe reflecting on itself. It's a thought worth resting with for a moment, not forcing it into some grand philosophical conclusion, just holding it gently. You are made of stardust, not as a poetic figure of speech, as a literal fact. Let your breath slow. Let your shoulders drop. You don't need to understand every detail. Just let the feeling of that vast history drift through you. Our own galaxy, the Milky Way, is home to somewhere between 200 billion and 400 billion stars. That range itself tells you something. We have not yet counted them all, and the uncertainty in our estimates spans hundreds of billions. The galaxy is a flattened disk about 100,000 light-years across, with a slight central bulge and spiral arms trailing outward in great curving arcs. Our solar system sits roughly 2/3 of the way from the center, in one of those quieter arms, orbiting the galactic center once roughly every 225 million years. The last time we were in our current position relative to the galactic center, dinosaurs were only just beginning to appear on Earth. The galaxy rotates. Every star in it is moving. The sun itself is moving through space at about 800,000 kilometers per hour relative to the galactic center. Everything in our solar system, every planet, every moon, every comet and asteroid, is carried along at that speed together as a unit. We don't feel this motion because there is nothing nearby to feel it against. Motion at this scale has no sensation. And beyond our galaxy, there are more, many more. Estimates suggest there are roughly 2 trillion galaxies in the observable universe. That is 2 followed by 12 zeros. Some are small, irregular clouds of stars. Some are enormous spirals similar to the Milky Way. Some are vast elliptical galaxies containing trillions of stars, the product of many earlier galaxies having collided and merged over billions of years. The distances between galaxies are so large that the light traveling between them takes millions. sometimes billions of years to arrive. When you look at the Andromeda galaxy on a clear dark night, a faint smudge of light in the constellation for which it is named, the light entering your eyes left that galaxy over 2 million years ago. You are looking into the past. That is not a figure of speech. The light that reaches your eye tonight departed Andromeda, when our ancestors were just beginning to make stone tools on the African savanna. Every telescope is a time machine. The farther we look, the further back we see. The most distant objects we have ever observed, ancient galaxies detected by instruments like the Hubble Space Telescope and now the James Webb Space Telescope, appear to us as they were when the universe was only a few 100 million years old. When we look at them, we are seeing the universe in its early youth. Young galaxies still forming, bursting with new stars, before the long quiet of settled cosmic middle age had set in. There is something very gentle in that. The universe has a history, a story. It began, it evolved, it grew complex over enormous stretches of time. And we are here, near the middle of that story as far as anyone can tell. Conscious enough to look back and wonder, you don't need to hold all of that tonight. Let the image of all those galaxies, all those turning islands of light, spread across an expanding space. Simply hover softly in your awareness. Let it be a backdrop rather than something you need to grasp. Now, within our own galaxy, let us spend a little while with stars. Because stars are worth understanding, even in the most general and gentle terms. Not because the details are necessary, but because the lives of stars are, in their way, beautiful. They follow a long, patient arc from birth through a long, stable middle life to a varied and often spectacular end. Stars are born inside enormous clouds of gas and dust, called nebulae. These clouds drift through the galaxy, sometimes disturbed by a nearby supernova shock wave or a slow collision with another cloud. When part of a cloud begins to collapse under its own gravity, the collapse feeds itself. As material falls inward, it heats up and the pressure rises. Eventually, if the collapsing cloud has enough mass, the temperature at the center reaches the point where hydrogen fusion can begin, and the cloud becomes a star. Once fusion begins, the star enters a long period of balance. The outward pressure from the energy of fusion pushes against the inward pull of gravity. The two forces hold each other in check. A star like our Sun can maintain this balance for roughly 10 billion years. The Sun is about 4.5 billion years old. It has about 5 billion years remaining in its main, stable phase of life. During those billions of years, the star slowly converts hydrogen in its core into helium. The core gradually becomes enriched in helium, and eventually, the hydrogen in the core begins to run out. The balance shifts. Gravity gains the upper hand, and the core begins to contract while the outer layers expand and cool, turning the star red and vastly larger. A star like our Sun will one day swell into what is called a red giant, large enough to engulf the inner planets of our solar system. But before that happens, in about 5 billion years from now, the Sun will be a steady warm star, very much like the one you know. Tonight, it is resting below your horizon, carrying its light to the other side of the world. And far above you, in the darkness between the stars, other suns are doing the same thing, living their long, quiet lives, fusing hydrogen, warming whatever worlds might orbit them. indifferent and serene. Breathe gently. You are in no hurry. The universe certainly isn't. Let the stillness of all those stars, millions and billions of them, settle over you like something soft. For stars more massive than the sun, the story ends differently. Massive stars burn their fuel much faster, living only a few million years compared to the sun's 10 billion. When they reach the end, the collapse is sudden and violent. The core falls inward in less than a second. The outer layers rebound from that collapse in a shock wave and are blasted into space in what is called a supernova explosion. For a brief time, perhaps weeks, a single dying star can outshine its entire host galaxy. All the billions of other stars in that galaxy, combined, outshone by one. The energy involved is staggering, though it is better not to picture it too vividly tonight. Suffice to say that supernovae are among the most significant events the universe produces. They scatter heavy elements, the elements that make planets and oceans and living things, into the surrounding space. They send shock waves through nearby gas clouds that can trigger new star formation. They are, in a real sense, acts of cosmic generosity. The death of one star seeding the birth of many others and of worlds, and perhaps of life. What remains after a supernova depends on how massive the original star was. Stars somewhat more massive than the Sun can leave behind a neutron star, an object so dense that it is made almost entirely of neutrons packed together, about 20 kilometers across, but containing more mass than the Sun. A teaspoon of neutron star material would weigh, on Earth, roughly 1 billion tons. The gravity at its surface is so strong that it measurably curves the path of light passing near it. Some neutron stars rotate very rapidly, emitting narrow beams of radiation that sweep around, like the beam of a lighthouse as the star spins. When Earth lies in the path of one of those sweeping beams, we detect a regular pulse of radio waves, arriving with almost clockwork precision. These objects are called pulsars, and some of them are so regular that they rival the best atomic clocks we have built. They have been used to test Einstein's theories of gravity with extraordinary precision. They have been used to search for low-frequency gravitational waves passing through the galaxy. And all of this is happening, quietly and continuously, in the space above your ceiling tonight. Pulsars spinning, supernovae scattering their gifts of matter, gas clouds collapsing into new stars somewhere in the galaxy. None of it demands your attention. None of it requires anything from you. It simply continues as it always has, in the vast and patient dark. Let your body rest. Let your mind drift where it wants. You don't need to follow every thought. Just let the images come and go. There are places in the universe where the nature of space and time themselves become strange, where the familiar laws that govern how things move and how time flows are bent almost beyond recognition. These places are worth spending a little time with, in a gentle and unhurried way, because they reveal something profound about the universe we inhabit. And profundity, encountered softly, can sometimes bring a kind of quiet peace. The most dramatic of these places are called black holes, and despite their reputation, they are worth approaching without alarm. A black hole is not a hole in the sense of an emptiness or an absence. It is, in fact, the opposite. It is a region where mass is so concentrated, and the curvature of space so extreme, that not even light can travel fast enough to escape from it. The boundary around this region is called the event horizon, and it is less a physical surface than an invisible threshold. If you were to cross it, nothing outside would look immediately different to you, but from that moment, every possible path you could take would lead further inward. There is no up that leads out. The geometry of space itself, inside the event horizon, does not permit escape. The nearest known black hole to Earth is several thousand light-years away. You are in no proximity to one, but their existence in the universe tells us something significant about the nature of gravity and space-time. Einstein's general theory of relativity, published in 1915, described gravity not as a force in the Newtonian sense, but as a curvature of space-time. Massive objects bend the fabric of space and time around them. Other objects, including light, follow the curvature of that fabric. This is why the sun bends the path of light from distant stars, an effect first measured during a solar eclipse in 1919 by the astronomer Arthur Eddington. The measurements matched Einstein's predictions and astonished the scientific world. Black holes are simply the most extreme expression of this curvature. They represent a region where space-time curves so severely that it closes in on itself. And in doing so, they reveal something that we don't fully understand yet. At the very center of a black hole, our current physics breaks down. The equations produce results that are not physically meaningful. Something happens there that our best theories cannot yet describe. That gap in understanding, that place where our best tools reach their limit, is one of the most honest and quietly beautiful things about science. The universe is not obligated to be fully comprehensible to us. It is not designed for our convenience. It simply is. And the fact that it still holds secrets, even after centuries of careful study, is in some ways a comfort. It means the universe is larger than our current understanding. It means there is still more to discover. You don't need to hold on to these ideas firmly. Let them drift. Let them blur at the edges the way thoughts do when sleep is beginning to arrive. The details don't matter tonight. The feeling of vastness is enough. There is a quality to deep space that is difficult to name precisely. It is not silence exactly, because silence is something we experience through an absence of sound, and sound cannot travel through the vacuum between stars. It is something more like a quality of patience, an enormous unhurriedness. The stars have been burning for billions of years. The galaxies have been turning for most of the age of the universe, and all of this vast activity, this extraordinary complexity of matter and energy and gravity and light, asks nothing of you. It simply continues. You are welcome to observe, or to drift away into sleep, and the universe will proceed either way, without judgment. Let that be a gentle thing. Not isolating, just spacious. Room to breathe. We were moving, a little while ago, through the lives of stars and the strange territories near black holes. Now let us drift a little further into one of the deeper mysteries that modern physics has uncovered. A mystery that touches something fundamental about what the universe is actually made of, and how most of it is, in a very real sense, invisible to us. For most of human history, when we looked up at the sky and asked what the universe was made of, the answer seemed clear. Stars and gas and dust. Light. Empty space between them. This was and still is a beautiful answer. but it turns out to be only a partial one. In the middle of the 20th century, astronomers began to notice something unusual when they studied galaxies. When they measured how fast stars at the outer edges of spiral galaxies were moving in their orbits, the numbers did not match the predictions. According to the theory of gravity, stars at the outer edges of a galaxy, where the mass of stars and gas is thin, should be moving more slowly in their orbits, just as the outer planets of the solar system move more slowly than the inner ones. Neptune moves much more slowly than Mercury, because it is far from the concentrated mass of the Sun at the center. But the stars at the outer edges of galaxies were not slowing down the way they should. They were moving almost as fast as stars closer to the center. Something was preventing them from slowing. Something was holding them in those faster than expected orbits. And that something could not be seen. The astronomer Vera Rubin, working with her colleague Kent Ford in the 1970s, made some of the most careful and persuasive measurements of this effect, studying many different galaxies and finding the same pattern repeatedly. The rotation curves, as they are called, were flat when they should have been falling. Something invisible was providing extra gravitational pull at the edges of galaxies. Rubin's work, building on earlier hints from astronomers like Fritz Zwicky decades before, helped establish this as a genuine and serious problem, not an observational error. What could it be? What invisible thing has enough mass to alter the orbits of entire galaxies? Physicists gave it a provisional name, dark matter, not because they know it is dark in the optical sense, but simply because it does not appear to emit or reflect or absorb any form of light that we have yet been able to detect. It does not shine, it does not glow, it cannot be seen. But through its gravitational influence on visible matter, its presence is revealed with considerable clarity. And the more astronomers looked, the more evidence they found. Not just in the rotation of individual galaxies, but in the way galaxies cluster together in groups and vast structures, in the way light from distant galaxies bends as it passes through those clusters far more than the visible mass alone would predict, in the way the earliest patterns of the cosmic microwave background are shaped. Every independent line of evidence pointed to the same conclusion. There is more matter in the universe than we can see, much more. Current estimates suggest that ordinary matter, everything made of atoms, all the stars and planets and gas and dust, and everything you have ever touched or seen, makes up only about 5% of the total energy content of the universe. Roughly 27% appears to be this unseen dark matter, and the remaining 68% is something even stranger, which we will come to in a little while. 5%. The universe that we can see, that we can touch, that we have built all of our science and all of our art and all of our lives from, is 5% of what is actually there. Let that settle gently. It is not a frightening thought. It is an astonishing one, but a quiet kind of astonishment. The universe is larger than we imagined, deeper, more populated with things we do not yet understand, and we are only beginning to find our way through its outer rooms. What is dark matter exactly? That physicists genuinely do not know, not yet. But there are thoughtful and careful ideas. One of the leading candidates for many years has been a class of hypothetical particles called WIMPs, which stands for weakly interacting massive particles. The idea is that dark matter might consist of particles that have mass and therefore gravity, but do not interact with ordinary matter through any of the other forces. They would pass through walls, through planets, through you, leaving no trace. Billions of them might be moving through your body right now, carrying no harm, leaving no mark, noticed by nothing. Underground detectors built deep inside mountains, and former minds have been searching for WIMPs for decades. Scientists cool their equipment to temperatures just above absolute zero, trying to eliminate every possible source of interference, and watch for the faintest possible signal of a WIMP occasionally bumping into an ordinary atomic nucleus. So far, those experiments have not detected anything conclusive. The silence is not a failure exactly. Each experiment that returns without a signal tells us something important about what dark matter is probably not. The parameter space of possibilities is slowly narrowed. There is another candidate called the action, a very light particle originally proposed not to explain dark matter, but to solve a different problem in particle physics. If actions exist, they would be extraordinarily light, enormously numerous, and would interact with ordinary matter in ways that might, under very specific conditions, produce a faint detectable signal. Experiments searching for actions, using strong magnetic fields and very sensitive microwave detectors, are underway in several countries, listening for a whisper from an invisible world. There is also a class of proposals that doesn't involve new particles at all, but instead suggests that our understanding of gravity might itself be incomplete. Perhaps on the scales of entire galaxies, gravity behaves slightly differently than Einstein's equations predict, in a way that mimics the effect of extra unseen mass. These modified gravity theories have had some successes in explaining the rotation of galaxies, but they have difficulty accounting for all the other lines of evidence that dark matter would naturally explain. Most physicists still lean toward the particle explanation, but the modified gravity ideas are not entirely ruled out. The honest answer, the one that physicists themselves will give you, is that we do not yet know what dark matter is. We know a great deal about what it does. We know how much of it there appears to be. We know where it seems to concentrate. We know it does not emit light. We know it behaves, in terms of its gravitational effects, as a smooth and enormous halo around galaxies, extending far beyond the visible disk of stars. But its fundamental nature remains unknown. And somehow that is all right. The universe is not required to offer up all its answers on our schedule. Science is patient in a way that mirrors the universe itself. Not anxious, not in a hurry. Just persistently, carefully curious. Let your thoughts drift if they want to. You don't need to remember any of these details. Just let them pass through, soft and slow. Now let us drift towards something that, if anything, is even stranger than dark matter. Something that doesn't just remain invisible to our instruments, but that actively pushes the universe apart. In the late 1990s, two groups of astronomers were doing something very careful and painstaking. They were measuring the distances and recession speeds of a particular type of exploding star, called a Type Ia supernova in very distant galaxies. Type Ia supernovae are remarkable because they always reach roughly the same peak brightness. This makes them useful as what astronomers call standard candles. If you know how bright something actually is, and you can measure how bright it appears from where you are, you can calculate how far away it is. The scientists were expecting their measurements to confirm something that seemed almost obvious. Yes, The universe has been expanding since the Big Bang. And yes, gravity should be gradually slowing that expansion. All that mass, all those galaxies pulling on each other across cosmic distances, should be putting the brakes on, bit by bit. The question they were trying to answer was simply how much the expansion was slowing. They expected to measure a deceleration. What they found instead was that the expansion was not slowing. It was speeding up. Distant galaxies were receding from us faster than the expansion rate implied by the earlier universe. Something was pushing space apart at an accelerating rate, and it was not anything in their models. It was not any known form of matter or energy. Both teams, independent of each other, reached the same conclusion. The leaders of both groups, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011 for this discovery. It was a discovery that, in a very real sense, overturned the expected story of the universe. Physicists gave this unknown something a name: dark energy. And the name is chosen carefully because it is honest in its vagueness. We don't know what it is. We only know what it does. It fills space uniformly. It does not dilute as the universe expands. Unlike ordinary matter or radiation, which spread thin as the volume of the universe grows, it has a consistent presence everywhere, in all of space. And its effect is to cause space itself to accelerate its expansion. The simplest mathematical description of dark energy is something called the cosmological constant, which Einstein himself originally introduced, for different reasons, into his equations of general relativity. He later called it his greatest mistake when it seemed unnecessary. It turns out it may not have been a mistake at all. In Einstein's equations, the cosmological constant represents a kind of intrinsic energy that belongs to empty space itself. Space is not truly empty. It has a tiny but non-zero energy density, and that energy, spread across the unimaginable volume of the observable universe, adds up to enough to drive accelerating expansion. But this explanation raises a problem of its own. When physicists try to calculate how large the cosmological constant should be from first principles, using quantum mechanics, they get an answer that is off from the observed value by a factor so large that it is difficult to even state clearly. The theoretical prediction and the observed value are wildly, almost comically mismatched. This discrepancy is sometimes called the worst prediction in physics, not because the underlying physics is wrong, but because we are missing something important in how we connect quantum theory to gravity at cosmological scales. Other possibilities for dark energy include something called a scalar field, a kind of energy that slowly changes over time in space. Some physicists call this quintessence, a name borrowed from the ancient philosophical idea of a fifth element underlying all matter. In these models, dark energy is not a fixed constant, but something dynamic, slowly evolving, and potentially different in the far past and the far future of the universe. Whether this is the case is something that future observations might be able to distinguish. None of this needs to be fully understood tonight. These are the kinds of ideas that physicists spend careers with, turning them over, testing them against data, looking for inconsistencies that might point towards something better. The important thing, the quiet and beautiful thing, is simply that the universe is doing something we did not expect. It is growing faster and faster, driven by an energy we cannot see, toward a future we cannot fully predict. And the scientists who study this do so with a steadiness that is itself a kind of calm. Not knowing is not a catastrophe. It is the normal condition of science. And it is, in a way, the normal condition of being conscious in a universe as large and complex as this one. Rest your body a little. Let your breathing settle. The universe will continue its expansion whether you follow every detail or not. There is something that follows from all of this dark matter and dark energy. Something that is worth sitting with quietly before we move on. When we add it all up, ordinary matter, the kind that makes atoms, that makes stars and planets, and everything you have ever touched or seen or loved, accounts for only about 5% of what the universe contains. The rest is invisible, undetectable by any telescope we currently have, present only as a gravitational whisper, or as the unexplained acceleration of a vast and expanding space. In other words, what we call the universe of light and matter and chemistry and life, is like a thin, visible layer on top of something much deeper and much larger that we barely understand. Our entire history, every civilization, every scientific discovery, every work of art, and every personal memory has taken place within that thin 5%. We have been exploring the lobby of a building whose upper floors we have not yet been able to enter. And somehow, that is not a diminishing thought. It is, in its own way, liberating. It means the universe is larger than we have yet explored. There is more. There is always more. And we are, slowly, finding our way toward it. You don't need to hold that thought tightly. Let it rest at the edge of your awareness, gentle and unhurried, the way a star rests at the edge of the visible sky. You don't need to reach it. It is enough that it is there. Let your body soften. Let your thoughts slow. We have a little further to drift together tonight. One of the most remarkable facts about the universe is that it has not always been the way it is now. Not just in the obvious sense that stars are born and die and galaxies evolve over billions of years, but in a deeper sense. The fundamental conditions that allow matter to exist at all, that allow atoms to form, that allow chemistry to occur, those conditions were not always present. They came into being gradually, in the moments and years and millennia after the Big Bang. In the first fractions of a second, the universe was so hot that not even protons and neutrons could hold themselves together. Everything was a kind of soup of more elementary particles, quarks and gluons, in a state of constant frantic collision. As the universe expanded and cooled, protons and neutrons condensed from this soup, and then, in the first few minutes, those protons and neutrons fused together into the first atomic nuclei. Hydrogen, mostly. Helium. Tiny traces of lithium. A process called Big Bang nucleosynthesis laid down the chemical foundation of the universe in those first minutes, and the proportions we observe today in the oldest stars match the predictions of that theory with remarkable precision. But there is a mystery buried in those first moments that physicists have not yet fully resolved, a mystery about why there is anything here at all. In the Big Bang, matter and antimatter were produced. Antimatter is, in every respect, the mirror image of ordinary matter. Every particle has a corresponding antiparticle. When a particle meets its antiparticle, they annihilate each other completely, converting their mass entirely into energy. Proton meets antiproton, they vanish into pure radiation. Electron meets positron, same result. In the early universe, matter and antimatter were produced together in enormous quantities. And by our best understanding of physics, they should have been produced in exactly equal amounts. If that were true, everything would have annihilated everything else, and the universe would contain nothing but radiation. No matter, no atoms, no stars, no planets, no life. But clearly, that is not what happened. There is matter. There is something rather than nothing. And the best answer physicists currently have is that in the first moments, by some process not yet fully understood, matter was produced in very slightly larger quantities than antimatter. By roughly 1 part in a billion. 1 extra particle of matter for every billion matter-antimatter pairs. And when all the annihilations were over, that tiny excess remained. That tiny remainder of 1 in a billion is everything. Every star, every galaxy, every atom in every body that has ever lived. We exist because of an asymmetry so small it was almost nothing, and we do not yet fully know why it exists. This question, why there is more matter than antimatter in the universe, is one of the deepest open problems in physics. There are candidate mechanisms, processes that could have generated a small imbalance between the two in the very early universe. The physics involved is at the frontier of both particle physics and cosmology. Experiments at places like the Large Hadron Collider at CERN study the small differences in behavior between particles and antiparticles, looking for clues. Progress is being made slowly and carefully, but the full answer is not yet known. And again, there is something quietly extraordinary in that. The reason you exist, the reason any of us exists, is connected to a tiny asymmetry in the very first fraction of a second of the universe. An asymmetry that science has identified but not yet fully explained. You are here because of a whisper in the physics of the Big Bang that we are still working to hear clearly. Let that be a thought that drifts rather than demands. You don't need to solve it tonight. No one does. It rests in the hands of patient scientists and patient time, and that is exactly where it belongs. Somewhere above you, at this moment, the sky is very dark. Even if clouds are overhead, even if the lights of a city are pushing upward into the air above your home, beyond all of that the cosmos continues, unchanged by your local conditions. Stars are where they were before your lights went out tonight. The Milky Way is arching across the sky, its diffuse pale band mostly invisible from most places on Earth's surface now, but present nonetheless. The nearest galaxies. The Magellanic Clouds visible from the southern hemisphere. The Andromeda Galaxy faintly accessible under the right conditions from anywhere in the northern hemisphere, are right where they have been for billions of years. Nothing in the sky tonight requires your attention. It simply continues, steady and untroubled. Let that image hold you for a moment. The sky above your roof. The uninterrupted dark between the stars. The extraordinary patience of it all. We have been drifting through some of the largest and deepest questions in modern cosmology. The invisible substance that gives galaxies their gravitational shape. The invisible energy that is accelerating the expansion of space. The tiny asymmetry between matter and antimatter that allowed us to exist at all. Each of these opens outward into further questions and those questions open into further ones still. The universe is not a puzzle with a finite number of pieces. It is more like a territory whose map keeps expanding the more carefully you explore it. Now let us visit some of the quieter and more intimate facts about the space we move through. The solar system. The world's near enough that we have actually sent machines to visit them. In some cases landed on them. In one case landed humans and brought them home. Our solar system consists of the Sun at its center, 8 planets and their moons, countless smaller bodies, belts of rock and ice, and the enormous diffuse shell called the Oort cloud that extends to perhaps a quarter of the distance to the nearest star. The whole system formed from a single collapsing cloud of gas and dust about 4.5 billion years ago. The Sun gathered most of the mass. The remaining material formed a disk, and within that disk, particles collided and stuck, and gradually accumulated into larger and larger bodies until the planets emerged. The inner rocky planets, Mercury, Venus, Earth, and Mars, formed close to the Sun, where temperatures were too high for ice to survive, so they are made mostly of rock and metal. The outer planets, Jupiter, Saturn, Uranus, and Neptune, formed beyond what astronomers call the frost line, where temperatures were low enough for ices to be stable, and they were able to accumulate much more material, becoming the gas and ice giants we know. Jupiter is by far the largest. It contains more mass than all the other planets combined. Its atmosphere is a swirling chaos of bands and storms. The most famous of these storms, the Great Red Spot, is a high-pressure region that has been observed continuously for at least 350 years, though it has been slowly shrinking over recent decades. It is still large enough to contain the entire disk of Earth within it. The winds inside it reach several hundred kilometers per hour. Jupiter's influence on the solar system extends far beyond its own atmosphere. Its immense gravity has shaped the asteroid belt, preventing the material there from ever coalescing into a planet. It deflects comets and asteroids that might otherwise threaten the inner solar system, acting as a kind of distant gravitational shepherd. Some researchers have proposed that Jupiter's presence may have been important in allowing stable long-term conditions to persist on Earth for long enough for complex life to evolve. Though the full picture is still a matter of debate among planetary scientists. Saturn is quieter in appearance than Jupiter, its pale cream and tan bands less vivid, but it is remarkable in a different way. Its ring system is among the most visually striking structures in the solar system. The rings are made mostly of water ice, ranging in size from tiny dust grains to blocks several meters across. They span an enormous distance, hundreds of thousands of kilometers from the planet, yet they are extraordinarily thin, often only tens of meters deep. The rings are not permanent. They are relatively young by planetary standards, perhaps only 100 million years old, and they are slowly losing material, both through the slow degradation by micrometeorite impacts and through what is called ring rain, a process by which charged particles from the Sun cause ring material to spiral down into Saturn's upper atmosphere. In perhaps 100 million years, the rings may be gone. On the scale of the solar system's age, that is not very long. We are living in a window of time when Saturn happens to have its most elaborate ring system. Future generations of any beings who might look up at Saturn from some vantage point in the solar system will see something different. The universe is continuously changing, even in its most apparently stable and permanent seeming features. The moons of the outer solar system are remarkable in their own right. Jupiter has 4 large moons, discovered by Galileo in 1610, that orbited in the same plane and visible even through a small telescope as points of light shifting position from night to night. Galileo's observation of these moons was one of the early confirmations that not everything in the sky orbits Earth, a key piece of evidence for the Copernican model of the solar system. One of those moons, Io, is the most volcanically active body in the solar system. Its surface is covered in sulfurous lava and active volcanoes, whose eruptions have been directly observed by spacecraft. This activity is driven by tidal heating. Io's orbit is slightly elliptical, and as it moves closer to, and then further from Jupiter's enormous gravity in each orbit, the planet's gravitational pull flexes the moon's interior, generating heat. The result is a world of constant geological upheaval, with no impact craters visible because fresh lava resurfaces the ground faster than craters can accumulate. Another of Jupiter's large moons, Europa, is covered in a smooth shell of ice. Beneath that ice, warmed by the same tidal heating that drives Io's volcanoes, there is believed to be a global ocean of liquid water, possibly deeper than Earth's oceans. Where there is liquid water, and where there is heat from hydrothermal activity on the ocean floor, some scientists suggest there might be conditions capable of supporting life. Not life like ours, nothing complex, but perhaps something resembling the microbial communities that thrive near hydrothermal vents at the bottom of Earth's oceans. NASA is developing a spacecraft called Europa Clipper to study the moon in detail, with a planned arrival in the early 2030s. Saturn's moon Titan has an atmosphere denser than Earth's, composed mostly of nitrogen with a complex chemistry driven by sunlight at the top of the atmosphere. Titan has lakes and rivers and rain, but they are made of liquid methane rather than water. Its surface temperature is roughly -179 degrees Celsius. It is one of the most alien environments in the solar system, yet in some ways it resembles a frozen, hydrocarbon version of early Earth in its atmospheric chemistry. Enceladus, another of Saturn's moons, has ice geysers erupting from its south pole, spraying water vapor and organic molecules into space. Instruments on the Cassini spacecraft, which orbited Saturn from 2004 to 2017, sampled this plume material and found complex organic molecules, including some that are found in the chemistry of life on Earth. All of these worlds are still here tonight, churning in the dark at enormous distances from your window. Titan drifting in its orbit around Saturn, Europa cycling around Jupiter in its 3.5-day orbit, Enceladus venting its quiet plumes into the cold void. You don't need to reach them. It is enough to know they are there. Little worlds with their own histories and their own quiet mysteries. Let your body rest. Let the details settle and blur. Just hold the feeling of all those worlds, all that variety and complexity, quietly orbiting in the dark above you. The question of whether life exists elsewhere in the universe is one that sits at the intersection of biology and chemistry and astronomy and philosophy. It is a question science cannot yet definitively answer, but what science has done, particularly in the last 3 decades, is transform our understanding of how common the basic conditions for life might be. Before 1995, we had no confirmed evidence of any planet outside our solar system. We assumed they existed, based on the logic that our solar system formed from a fairly ordinary process, and there was no reason to think it was unique. But we had no proof. Then, in 1995, the astronomers Michel Mayor and Didier Queloz announced the detection of a planet orbiting the star 51 Pegasi, about 50 light-years from Earth. It was a large planet, roughly half the mass of Jupiter, orbiting much closer to its star than any planet in our own system. Its presence was detected through the slight wobble it produced in the motion of its star, a wobble that could be measured in the shift of the star's light. Since then, thousands of planets beyond our solar system have been confirmed, with thousands more candidates awaiting final verification. The Kepler Space Telescope, launched in 2009 and retired in 2018, stared at a single patch of sky and detected planets by measuring the faint dimming of starlight when a planet passed in front of its star. It found them in astonishing numbers. From the statistics of Kepler's observations, astronomers have estimated that almost every star in the Milky Way hosts at least one planet. In a galaxy of hundreds of billions of stars, that implies hundreds of billions of planets, many of them rocky, many of them in the temperature range where liquid water might exist on their surfaces. Whether liquid water leads to life is something we don't fully know. Life on Earth arose in water, and all known life requires it. But whether that makes water a universal requirement for life, or simply a particular solution to the chemistry of life that happened to work here, is an open question. There may be forms of chemistry that could support life in very different solvents, under very different conditions. Titan, with its liquid methane, is sometimes offered as a thought experiment in this direction. We don't know if life could arise there. But the question is not obviously absurd. What we do know is that the building blocks of chemistry are everywhere. Complex organic molecules, including amino acids, which are the components of proteins, have been found in meteorites, in comets, in the clouds of interstellar gas that drift between the stars. The chemistry that leads toward life seems to be something the universe makes readily, wherever the conditions are even slightly favorable. Whether that chemistry actually crosses the threshold into self-replicating, evolving life is the step we cannot yet trace from first principles. The James Webb Space Telescope, launched in late 2021, and now operating at its observing position roughly 1.5 million kilometers from Earth, can analyze the atmospheres of some exoplanets when they pass in front of their stars. The starlight that filters through the planet's atmosphere carries chemical fingerprints, and by analyzing those fingerprints, scientists can determine what molecules are present in the atmosphere. If we ever detected oxygen and methane together in the atmosphere of a rocky planet, in a habitable zone, that would be very significant. On Earth, those two gases react with each other and would quickly disappear if they were not continuously replenished by biological processes. Finding both simultaneously in an exoplanet's atmosphere would suggest something is producing them. Something active, possibly alive. That detection has not been made yet. But we are in the early stages of being able to make it. The search is genuine and ongoing. And the answer, when it comes, will be one of the most significant in the history of science. There is something very peaceful about not yet knowing. The question of whether we are alone in the universe is open. And there is a kind of spaciousness in an open question. It has not yet become a fact. It is still a possibility, shimmering at the edge of our understanding. You can rest in the uncertainty of it without needing it resolved tonight. Let your mind drift. You don't need to reach a conclusion. the universe will not demand one from you. Now let us spend a little time with something that sits at the boundary between science and pure wonder: the nature of space and time themselves. Because one of the most important things that physics learned in the 20th century is that space and time are not the fixed, unchanging backdrop that common sense suggests. They are dynamic. They can be stretched, curved, and even measured to pass at different rates, depending on conditions. Einstein's special theory of relativity, published in 1905, introduced the idea that the speed of light is constant for all observers, regardless of how they are moving. This sounds like a modest technical statement, but its consequences are far-reaching. If the speed of light is always the same, then time itself must be able to vary. A clock moving very fast relative to you will tick more slowly than a clock at rest beside you. This is not a mechanical effect, not something happening to the clock's gears. It is a genuine difference in the rate at which time itself passes. The faster you move, the slower your time flows relative to someone who is stationary. This effect, called time dilation, has been directly measured. Atomic clocks flown on fast aircraft tick slightly more slowly than identical clocks left on the ground. The difference is tiny at everyday speeds, but it is real and measurable. The GPS satellites orbiting Earth must have their clocks corrected for relativistic effects, both from their speed and from the weaker gravity at their altitude, or they would accumulate errors that would make the GPS system useless within hours. The General Theory of Relativity, published in 1915, extended these ideas to gravity. In strong gravitational fields, time also slows. A clock near a massive object ticks more slowly than a clock far from any mass. Near the event horizon of a black hole, this effect becomes extreme. An observer far away watching something fall toward a black hole would see it appear to slow down as it approached the horizon, its light growing increasingly red-shifted, appearing to take an infinite amount of time to cross the boundary. From the falling object's own perspective, nothing unusual happens at the crossing. Time passes normally. The geometry of the situation means these two perspectives are both valid, and reconciling them fully is one of the deep puzzles at the heart of modern theoretical physics. What all of this means, taken together, is that time is not a river flowing at one constant speed through an absolute, universal channel. It is something woven into the fabric of space itself, flexible, dependent on local conditions, different at different places, and in different states of motion. The present moment you are experiencing right now, lying still in your room, is genuinely different from the present moment of a particle moving near the speed of light, or a particle deep in a gravitational well. This is not philosophy, it is physics, confirmed by experiment, and this realization, that time is local rather than universal, that there is no single cosmic clock ticking in synchrony everywhere, is one of the most quietly profound things that science has established. The universe does not have one time. It has countless local times, each flowing at its own rate, shaped by mass and motion. You exist in your own little bubble of time, defined by the gentle gravity of Earth and your own very slow velocity relative to the universe's large structures. And within that bubble, this moment, this quiet and restful moment as you lie in the dark, is genuinely, physically yours. That is a beautiful thing. Yours. Just this. Just now. Breathe. Let your thoughts soften. Let the images of galaxies and moons and relativistic clocks settle into something gentler. You don't need to hold the details. The feeling of the idea is enough. Space is not empty. This is worth saying carefully, because the word empty is one we use loosely, and space seems to match it. Between the stars, between the galaxies, the distances are almost unimaginable, and the matter within them is extraordinarily thin. If you compressed all the matter in the Milky Way galaxy into a sphere, leaving out all the empty space between the stars, that sphere would be tiny compared to the galaxy itself. Space is, by any everyday measure, almost entirely empty, and yet it is not nothing. Even in the most isolated regions of intergalactic space, far from any star or galaxy, there is still the cosmic microwave background radiation flowing through from all directions. There is still the solar wind from distant stars, though it has weakened to almost nothing. There are cosmic rays, high-energy particles produced by supernovae and other energetic events, streaming through at close to the speed of light. There are neutrinos, almost massless particles produced in stellar cores and supernova explosions, in such enormous numbers that roughly 65 billion of them pass through every square centimeter of your body every second. They interact with ordinary matter so rarely that virtually all of them pass through the entire Earth without interacting at all. And then there is the quantum vacuum. Even in the complete absence of any particles or radiation, quantum mechanics tells us that space is not truly quiescent. At the smallest scales, virtual particles constantly flicker in and out of existence, brief manifestations of the Heisenberg uncertainty principle. These are not permanent particles. They appear and disappear too quickly to be directly observed, but they have measurable consequences. The Casimir effect, in which two very close metal plates experience a tiny attractive force in a vacuum, is one experimental confirmation that the quantum vacuum is not nothing, but has a kind of restless microactivity. What this means for dark energy is one of the deepest unsolved problems in physics, as we touched on earlier. But for now, the simple point is this. Space, even apparently empty space, is full of things. Of radiation and particles and quantum fluctuations and gravitational waves propagating from distant events. The darkness between the stars is not absence. It is a kind of fullness that we cannot see. Rest in that. Let the feeling of a full darkness settle around you. You are not in nothing. You are in space, which is full of things you cannot see. And those things have always been there, quiet and constant, long before you were born and long after any single life ends. Let that be a gentle thought rather than a large one. You don't need to grasp it. Just let it be there, like the darkness itself. Present and unhurried, we have drifted a long way tonight, from the first moments after the Big Bang, through the lives of stars and the mysteries of dark matter and dark energy, through the worlds of the outer solar system, and the question of life beyond Earth, through the strange flexibility of time itself, and the quiet fullness of apparently empty space. There is more we could visit. The universe contains more than any single night could hold, but there is something appropriate about stopping short of everything, about leaving the horizon open and unreached. Let us spend a little time now with the researchers and instruments that are currently trying to push the edge of our understanding further. Not because you need to follow each detail, but because there is something very calming about the image of human patience and persistence turn toward the cosmos. People spending careers looking for a signal that might not come, and finding it beautiful work regardless. Deep underground in several countries, in tunnels and caverns, carved into mountain ranges, embedded beneath former mines, ultrasensitive detectors wait in the dark. They are searching for dark matter particles. The detectors are cooled to temperatures near absolute zero to reduce the thermal noise that would otherwise swamp any faint signal. They are surrounded by layers of shielding, water tanks, layers of metal, the rock of the mountain itself, all designed to filter out the cosmic rays and other particles that stream through everything at the surface. The goal is to get as close to complete quiet as physically possible, so that if a dark matter particle happened to nudge one atom in the detector, the resulting tiny vibration could be noticed. These experiments have been running for years, sometimes for decades. The most sensitive of them, experiments with names like Lux Zeppelin, based deep in a former gold mine in South Dakota, or Pandax in China, or Xenont under the Gran Sasso Mountain in Italy, have progressively ruled out larger and larger swaths of the parameter space where WIMPs might hide. They have not yet found anything, but each non-detection is a genuine scientific result. It means dark matter, if it exists as a WIMP-like particle, is either lighter or heavier than previously expected, or interacts more weakly with ordinary matter than some models predicted. In parallel, radio astronomers using large telescope arrays are searching for actions, those light hypothetical particles that might solve two problems in physics at once. Experiments with evocative names like ADMX and Haystack use tunable microwave resonators immersed in strong magnetic fields to search for the faint signal that an action would produce if it converted into a photon in the presence of the magnetic field. The search proceeds frequency by frequency, like tuning through radio stations, looking for a whisper in the static. Overhead, satellites and balloons continue to map the cosmic microwave background with ever-increasing precision. The Planck satellite, a joint European Space Agency mission that operated from 2009 to 2013, produced the most detailed map of the cosmic microwave background yet made, revealing temperature variations of a few hundred millionths of a degree across the entire sky. Those tiny variations encode the distribution of matter and energy in the early universe, and from them, physicists have been able to determine the age of the universe, its geometry, the proportions of ordinary matter, and dark energy, and many other properties, all from a careful reading of this ancient, gentle, everywhere present afterglow. Future missions plan to go further, measuring not just the temperature variations in the cosmic microwave background, but the subtle polarization of that ancient light, which carries information about the very earliest moments of the universe, and potentially about the gravitational waves produced during cosmic inflation. Cosmic inflation itself is a hypothesis about an extraordinarily brief period just after the Big Bang, when the universe expanded at an almost incomprehensibly rapid rate. It was proposed by the physicist Alan Guth in 1980 as a way of explaining several otherwise puzzling features of the observable universe. Why does the cosmic microwave background have almost exactly the same temperature in every direction, even from regions that would not have had time to exchange heat by the time that light was released? Why does space appear to be almost perfectly flat on the largest scales? Inflation offers a solution. If space underwent a dramatic expansion very early on, Regions that were originally close enough to have reached thermal equilibrium were spread far apart. The flatness would be a natural consequence of that enormous stretching. Inflation is widely accepted as the most plausible framework. But the details of how exactly it happened, what field drove it, and whether there are consequences we could detect, remain active areas of research. If inflation produced gravitational waves, those waves would have left a specific pattern in the polarization of the cosmic microwave background. Detecting that pattern would be a direct window into the very first moments of the universe's existence, into physics at energies so extreme that they have never been approached in any laboratory on Earth. Gravitational waves themselves are a relatively new addition to our observational toolkit. Predicted by Einstein in 1916, but not detected until 2015, they are ripples in the fabric of space-time produced by the acceleration of large masses. The detectors that found them, LIGO in the United States and Virgo in Europe, are extraordinary instruments. They measure changes in distance between their mirrors caused by passing gravitational waves. These changes are smaller than 1,000th of the diameter of a proton. The sensitivity required to detect them is almost beyond imagining. The first detection was of two black holes, each about 30 times the mass of the Sun, spiraling together and merging about 1 billion light-years away. The entire event lasted only a fraction of a second in the data, a brief chirp in the noise. But it was real, and it was the first direct observation of black holes in the act of merging. Since then, dozens of events have been detected, including collisions between neutron stars, which also produce light and allow astronomers to observe the same event simultaneously in gravitational waves and in conventional electromagnetic radiation. The future of gravitational wave astronomy lies partly in space. A proposed mission called LISA, the Laser Interferometer Space Antenna, would consist of 3 spacecraft separated by millions of kilometers, forming an enormous triangle in space, and measuring gravitational waves at frequencies that ground-based detectors cannot reach. This would allow the detection of the gravitational waves produced by the slow spiral of supermassive black holes in merging galaxies, events that unfold over millions of years. It would also potentially detect gravitational waves from the very early universe, those primordial ripples from the epoch of cosmic inflation. All of this is ongoing. All of it is patient. Scientists check their instruments, analyze their data, write their papers, hold their conferences, update their models, and gradually, carefully, the picture of the universe grows clearer. The pace of discovery is not urgent. It is measured and steady, like the turning of galaxies themselves. And there is something deeply reassuring about that. The universe is not going anywhere. The questions are not going anywhere. The researchers working on them will pass their work to the next generation, who will pass it on again, and slowly, over lifetimes and centuries, the map of the cosmos will be drawn more completely. You don't need to see the finished map tonight. No one does. The map is enough work for all of human history and beyond. For tonight, all you need is the feeling of a vast, interesting universe continuing quietly above your roof, tended by patient minds, slowly becoming less mysterious, while remaining, perhaps always, mysterious enough. Let the images begin to blur a little, if they haven't already. You have wandered a long way tonight, from the first light after the Big Bang to the modern instruments, listening for the quietest whispers of distant events. You don't need to hold any of it tightly. Let it all loosen in your mind. Let the galaxies go. Let the dark matter clouds disperse. Let the gravitational waves pass through you without a trace, as they always do, carrying their news from distant collisions to some farther point. There are one or two quiet things left to say, and then you should simply let yourself drift. The universe, for all its vastness, produced you. Not as a plan, not as a goal, but as one of an infinite variety of outcomes that fell out of 14 billion years of matter and energy following their own rules. The specific arrangement of atoms that makes you who you are is extraordinarily improbable in the abstract. And yet here it is, here you are, breathing slowly in a room, on a planet, in a solar system, in a galaxy, in an observable universe that extends 46 billion light years in every direction from the point where you are lying right now. You are not separate from any of that. The hydrogen in your water forged in the first minutes of the universe. The carbon in your body made inside a star that died before the sun was born. The iron in your blood produced in the core of another star that ended in a supernova that scattered its elements across space, and eventually, over hundreds of millions of years, those elements became part of the cloud that became our solar system, and eventually part of you. There is no clean boundary between you and the rest of the universe. The atoms that are you today were part of something else before, and will be part of something else again. You are a temporary arrangement of matter that has been here for billions of years, and will be here for billions more. That is not a sad thought. It is, if you let it be, a very peaceful one. You are not lost in the universe. You are the universe looking at itself for a while, in a particular way, from a particular place. And for now, the particular place is a bed, and the particular way is with eyes closing, and the universe, as always, is perfectly content to let you rest. The questions we visited tonight: what dark matter is, what dark energy truly means, why there is matter rather than nothing, whether life exists elsewhere, what happens at the center of a black hole. These questions will remain open when you wake. They were open before you lay down. They have been open for decades, in some cases for centuries. They will still be there, patient and interesting, when you are ready for them again, but right now, they don't need your attention. Right now, the only thing asked of you is to breathe, to let your body be heavy, to let your thoughts become looser, more scattered, less attached to any particular thread. The Milky Way is arching above you right now. 100,000 light years of stars and gas and dark matter and mystery, and right at its edge, our unremarkable solar system, and at the surface of the third planet from the sun, you, breathing, still, beginning to rest. The universe has been here for 14 billion years, and will continue for an almost incomprehensible time beyond this moment. You are a brief and beautiful part of it. And this, right here, this soft darkness and this slowing breath, is as much a part of the universe as anything else. As much as a quasar blazing at the edge of the observable sky. As much as a neutron star spinning hundreds of times per second in the far distance. As much as the cosmic microwave background drifting through all of space, in all directions, forever. You are part of this. And this is yours, the quiet, the dark, the rest. If these gentle journeys through the cosmos help you drift, you are always welcome to return to deep somna whenever you need to find your way back to stillness. Sleep well. The universe is here. You are here. That is everything, and it is enough.